Hi, welcome to session 211. So this is entitled Advanced Toolchain Usage, parts 3 and 4. This is part 4. This is a continuation of the previous session that we just had, which is a continuation of a larger series of presentations on advanced toolchain topics, advanced toolchain usage topics. My name is Ryan Arnold. I am the engineering manager for the Linaro Toolchain Working Group. With me here today is Will Newton, a toolchain engineer, and he is going to continue the discussion we were having earlier. So here you are, Will.
Thanks. Yeah, in the last Connect, we did a lot of coverage of GCC optimization options, things like that, how to make your code go faster with options to GCC. So this time out, I'd like to cover a few useful options that the GNU link has got to sort of improve your code's performance and size and whatnot. Basically, I'll be covering reducing the number of global symbols you've got, section garbage collection, and the GNU symbol hash, which all provide similar benefits, typically improving your startup time and reducing the size of your executables, which obviously can improve performance too. So reducing the number of global symbols in your objects gives you a few benefits. It reduces the startup time because it reduces the amount of time the dynamic link has to spend fixing stuff up. It makes your function calls faster. If you can call directly within your object rather than going through a PLT, the performance will be better. And it reduces the size of your binaries on disk. The symbol tables are smaller, there's fewer relocations, the whole thing just gets smaller and tighter. So there's a few different ways you can do this. You can use a version script, which will let you turn all your global symbols into local symbols using globs. GCC has an F visibility equals hidden option, which will force your symbols to be hidden by default, and LD has an option -B symbolic, which will cover. So here's a contrived little example with a function in a library and then another function, which we could have in this case just made that help function static and this whole thing would go away, but we like to make our lives difficult, so we didn't do that. I mean, this is basically if you've got two different files, then you can't make the helper function static. So you would need to have it global for that reason. So it's not an entirely implausible scenario. So if you build this code as is, this is what you get in your symbol table. Lots of junk. That's from the CRT basically, and the default linker script. But as you can see, there's a helper functions there, and the library function is there. So essentially, we don't really feel like that helper function should be in that list. So this is what a linker version script looks like. Using this, what we're saying there is we want all symbols that start with liba underscore to be global, and everything else, we want that to be considered local. And we're also applying a version to the symbols, which is probably episode 5 of this advanced toolchain session. And this is what happens when we pass that version script to the linker. So we're just using the compiler driver to pass version scripts and then this file to the linker, and then lots of things have now disappeared. We've still got a bit of gunk from the CRT, but now we just have libafunc on its own with the appropriate version in there. You can kind of ignore the version for these purposes, but essentially we've hidden that helper symbol. B symbolic is I'd like to say relatively recent, but it's actually quite old now, feature of the linker that will help you make your function calls local to an object. there's a few issues with the way it operates, because if you are calling a truly global symbol, then you want it to be preemptible. That is, you want to be able to, if you load another shared library that also implements that symbol, you might want that. So say something like malloc in the C library, if you LD preload a malloc implementation, you want everything to use that version of malloc. You don't want some things to go, oh, I know that my version of malloc is actually in this object, I'll just call it directly. And also pointer comparison is affected by Symbolic, which means that if you do odd things like compare two function pointers for equality, and you've pulled the Symbolic flag on the linker, that comparison might not work anymore. But it's really a corner case. It's not something that you will commonly do.
So you use it when you know that your functions are safe. You don't use it to compile glibc with, right?
Yeah, I mean, compiling glibc would cause lots of bad things to happen. So here we've got a library that's built from two files, and there's one function in each file, and they call each other. So this is similar to what we had in the previous example. And there you see function 1's calling function 2, but the way it does it is it does a BLX to init plus 0x38, which that's right up at the start of the shared object, which will be a PLT entry, which similar to what Ryan showed in the first session. And then in the symbol table, we have func2 with a jump slot relocation, which means the linker's got to do a little bit of work there to fix that up. If we pass Symbolic functions, then as you can see, the code generated, instead of doing a BLX into the PLT, it just does a BL straight to function 2, which is obviously a lot quicker, a lot simpler. And if we look in the symbol table, function 2 has disappeared, so less work for the linker to do.
Yeah, why BL, simple BL is faster than BLX?
Well, the reason it does BL rather than BLX is because it knows that it's going to thumb code. It knows it's staying within thumb, rather than going to the PLTs, which will be in ARM mode. Which I don't, there may be penalties for doing BLX rather than BL, I don't know. Yeah.
So in both cases, we have here not jump by address. We had direct jumps.
Yeah. Yeah, it would only help you with direct calls. Indirect calls are going to be slow and horrible as usual. So, anyone else questions?
What is the main reason for doing this optimization? Speed, size, something else?
It reduces the number of it reduces the amount of work the linker's got to do, so it's startup time, and then also the performance of your function calls. So if you're doing lots of calls within an object, it will make it considerably quicker.
Are there any implications as far as C++ programs and virtual functions?
Virtual functions are indirect calls. I'll go through a vtable. Probably. Any compiler writers in the house? Do you have a question? Oh, fair enough. Okay, well, I'll move on to section garbage collection, which is another linker feature which will reduce the size of your executable. LD can drop unused input sections when it does a final link. essentially it creates a graph of references between all the various sections in the link and figures out if there's anything that isn't referenced by any other section, then it can safely drop it on the floor. It starts the graph with the entry point, which will be your underscore start symbol usually, and just sort of goes from there. So it's if you've got a very large executable and it's got stuff in it that is only required in certain configurations and things like that, then you might have lots of code that's lying around that isn't actually very useful. So to apply this, it's best to compile with F function sections. This means that every function gets put in its own ELF section. Typically, you get one text section per file, so if you've got like 100 functions in a file, you get one section with 100 functions in it. Obviously, that reduces the granularity with which you can build this graph of references. So if you do F function sections, every function gets its own section, so one file could have 100 sections, one per function. At that point, you also have to pull GC sections on the linker, which will do this calculation of what sections it can throw away.
So, what conditions should be true for a function to get discarded from the final file?
If it's not referenced anywhere.
So code will be just removed. It will not be just that. It will be completely removed.
Yeah, that whole section will not be present in the final link. But the way ELF works, it can only operate on full sections. And as I say, typically, you will get more than one function in a section. So without function sections, the efficacy of GC sections is quite considerably reduced. There has been patches to apply this to the kernel, which I think give quite decent wins, about 5% code size reduction. Last I checked, they hadn't been upstreamed though.
Would it be better just to find? Wouldn't it be better just to find what functions are not called and why they are still there?
Ideally, yeah. I mean, I guess it's situations where you've got like tons of if-defs in a file, and it's just like instead of like if-defing everything, just drop the bits on the floor you don't need. But yeah, it would be better just to write really good code in the first place.
Actually, the information is in the bottom of the map file, so it will tell you which sections it will remove.
Okay, yeah, that's a good idea.
If you're working embedded with static links, it's what you do to libraries to make them work better when they link.
Yeah.
You don't want to get rid of code from the library to make it better. That's not how libraries work.
Depends on the library. Right, so the next thing is GNU symbol hash, which is, as the name suggests, is a GNU extension to the linker and glibc that instead of using the standard ELF hash for symbol names, uses a different function that has better performance characteristics. The ELF hash is used whenever you look up a symbol, so the dynamic linker will hash the symbol name, look up in its internal data structures what the address of that symbol is when you're doing things like symbol resolution at runtime. It's not just a better hash function, it also adds a thing called Bloom filters, which are kind of like hash functions, which let you do a quick check on a hash chain without having to walk all the way down it as to whether something's in it or not. And there's also a sorting step which improves the cache locality of symbol lookups. So it's very easy to enable. You just pull --# hash style equals GNU on LD. You can also do hash style equals both, which will put two separate hash sections in your object, but that obviously is going to improve this. Sorry, not improve. If you have both hash sections in there, your executable is going to get bigger, but will be more compatible with people who haven't got a dynamic linker capable of supporting it. Typically, every system that has glibc will support GNU hash. So Ubuntu, Fedora, all those will be good. Android, however, doesn't support GNU hash. So you're out of luck if you're on that platform.
So given that we already have a dependency on glibc, so why can't we enable hash style GNU by default whenever we are compiling against, linking against the glibc?
I'm not sure. A lot of distros do enable it by default, because it is just an easy win, really. I believe Linaro has had patches to add GNU hash to the Android linker, but I don't know what happened to those patches. But it's certainly something that's worth experimenting with, because it's quite low effort for quite reasonable rewards. Particularly Android doesn't pre-link anymore, so.
Again, rewards are speed or size?
Speed.
Speed for
startup and symbol resolution.
Yeah.
So yeah. So any dynamic call, the first time out, as Ryan discussed in the previous session, you have to do your symbol resolution, so that'll get quicker, and also your startup time will get quicker. So I'll hand over to Yvan to do GCC attributes.
Thank you, Will. Hi. I will present you some slides on GCC attributes. So first, let's see who in the room is familiar with the attributes in GCC. Okay. Who is using them? Okay. So pretty all the people that are aware of attributes are using them. That's a good thing. What are the attributes? First, they are a language extension. This is not ISO-C. It is known as GNU-C. And attributes are used to give directives and information to the compiler. And the way this information is used is to improve the verifications of your code, to have an impact on the way your code will be used, or to apply some optimization on your code. This will be used on different kind of construction in your code, on functions, types, variables, labels. And the syntax is this wonderful one with 2 underscore attributes, double underscore, and double parentheses, and the kind of attributes. Yes?
Is it C11 as well?
Yes, that's the second one.
now it is.
Now it is. So the support for the attributes was added into C++11. This time you have a new shiny syntax for attributes. So only a part of them were really added into the standard, and you can still call the GCC attributes, for instance, with this syntax, GNU : and the attribute's name. We will see after.
The
Yep.
semantics
Yep.
of the added attributes, are they exactly the same, slightly the same?
We will see there is very few attributes that were added into the standard, and the ones that were added are the same, yes.
Okay.
So in the slide, if you look at the presentation after, you have some pointers on the GCC documentation where you can see actually the manual on the attributes usage. I've prepared the presentation with different kind of attributes depending on the usage they will be used. First, for compile time checking to improve the validation of your code, the way your code will be used, optimization, ARM related, and the others. Let's start with compile time checking. here we have these three first attributes, error warning deprecated, that are applied on functions, or in the case of deprecated, on variables and types. So this one was added into the standard in the C++ 14. And the goal of these attributes is to raise compile time warnings or errors on some constructions. So for instance, here we have a small code with a type that is defined as attribute deprecated, and this functions is attribute error, and once we are compiling the code, we will have some warning on or some errors raised depending of the kind of attribute. Yes?
So can I put attributes on declarations of functions in the standard library? Like, I don't want to have any put as calls in my application. So can I declare put as with error attribute?
Yes, you can do that, and it will raise some errors at compile time, just to check that you are using this this function.
You mean you want to put the warning in the library code?
No,
No,
you put extern the call of the function, attributes error, and if during the compilation the compiler see that you do a call to this function, it will raise an error. Yes? Fish?
I mean, can it be used in such cases where you're changing the API of the library and in the future you don't want it people to use that particular function, right?
Yeah.
That's when you use
Yes, yes. The use case is really for code refactoring, etc. Or you can even use that to implement some, with kind of macros, some assertions to verify your code. It's kind of tricky, but it can be used for that. The next kind of attributes are the ones that are applying on functions, variadic or printf-like functions to do extra argument checking. You have the format arg, non-null, and sentinel. This is really useful when in your code you want to add some, for instance, debug functions where you can pass some level of debug, etc. And this function will act as printf. And if you don't use the attributes, when you have your string format that will be used, the compiler will not do any verification of the kind of arguments you passed to your functions. With that kind of attributes, you will add the information that this parameter is a string format. It will act as a printf function, and the arguments will start at the third argument. And here, if in the core of our function, when we call the function, if the parameters are not used properly, the compiler will raise a warning that the arguments are not used as they should be in printf. So each time you do that kind of code that acts like printf, like fscanf, etc., you should use that kind of attributes. It will do extra verification, and it is really useful. Another compile time checking is attributes warn unused results. Okay, so the behavior is pretty obvious. You will just point that you want GCC to raise the warning if the result of this function is not used. In this example, GCC will warn on this line because here the call to the function, the result is not used, whereas it is used in this line. So these attributes are really useful to enhance the validation of your code. The next one is named code usage. The term is not really well, but Let's see. The first are really related to what Will just present on the linker. It's just information to pass to the linker, like the section attribute or the visibility. And the first one are alias or weak and weak ref. These attributes can apply on function types for the visibility variables, and they are mostly used by libraries programmer to give default implementation or optimize version of the function, etc. In this example, we have a main part that will just read a character from the input, and we have some implementation of two functions, foo and bar, that are weak reference, weak alias to an ob function that just do nothing. Okay, so it is a default implementation. If we are compiling this program and executing it and put the sequence of character f, b, b, q, it will call the nop function each time. If we are giving another piece of code that will just provide an implementation of foo and bar, just recompiling it with this code will this time call the new implementation of the function. Okay, so this is useful when you are doing libraries or when you are developing your code and you just have stub of what will be defined later, and you just want to put the call to the function and give an information that it is not yet implemented or it has to be implemented later. Okay.
So, I want to make a comment that attributes from this section are mostly about interoperating with the linker. So they don't do that much on the compiler side, but they instrument, give linker hints how to link the final program.
Yes, it's really what I put.
Can this technique be used for, like, you know, I'm running on an ARM system and I know that this, you know, this particular version of ARM has this optimized function. Can I use that in that particular case instead of using function pointers?
There is a better way.
Yes, there is a better one. That is just the one next, which is this one, the ifunc. It is an indirect function support that was added into the ELF 2 years ago. 2009. Oh, already? Damn. So the ifunc, yes. The ifunc are really used for what you said, to provide optimized, dedicated code for the core you are running on. Okay, and this is chosen at link time.
Runtime.
Hmm?
Runtime.
Yeah. Yes. It is a linker, an ELF extension, and it provides dynamic relocation, and it is chosen at runtime. For instance, here we can define that foo function is an ifunc of a function f choice that will do that will resolve which function to execute. We have two functions, foo v4 and foo v3, which will do some stuff. And here, in this function, we will look into the hardware caps. Okay, what are the capabilities of the core we are running on? And if we are, for instance, on ARM with VFP v4, we will call foo v4 or foo v3. Okay, and in the main, you just have to call the foo function with the attribute function on it, so and it will work.
You seem puzzled. So the difference there is that if you didn't have the attribute, it will always call the f choice function every time you call foo, right? With that one, you only choose v3 or v4 at the first time you call the function, all the subsequent times you called the function directly. That's what ifunc is doing there.
So it avoids having to like declare tables and stuff.
Yeah, yeah. So you don't have to do any of this. This is done in the dynamic linker.
It puts the resolve address in that PLT slot.
Yeah, it's the same thing as a PLT resolver for library
Yep.
functions.
Is it press save?
Yeah. And before this attribute, you used to have to put inline assembly to do the ifunc mechanism. Now with the attributes, GCC will do it for you.
Can you repeat the question, please? What was the question?
If it is thread safe,
Thread safe. And it is or is not?
it is.
Well, you could write a non-thread safe resolver, but that would be your own problem.
You can write back code anytime.
Yeah, of course.
Is it a just-in-time resolve, or is it done by the dynamic linker as it's doing the dynamic link?
Will, I think you did it.
As in, will the call to F choice be made in the call stack underneath main when you first call foo, or before you hit start in the dynamic link code?
It's typically done lazily.
Lazy.
Yeah.
I think you can force it to be.
So this is like a user-specific PLT. So you tell this is my resolver for this specific symbol instead of going
Yeah,
to
but the resolver could be called at different points in the execution.
I think it depends on LD bind or not.
Yeah.
So
And also static, because static objects, you have to do a sort of emulation of PLT type stuff.
Okay. The next ones are constructor, destructor, and cleanup. This is pretty obvious. When you put a constructor attribute on a function, it will be called before the main, and the destructor will be called after the main or the exit of your program. You can pass priority to.
This is like init and fini sections.
And this one, the cleanup, applies on variables, and you specify that for one variable, which function to call when the variable's life goes out of scope. Okay.
is
So-
it for global variables, local variables, or which ones?
Depends. I think global variables is useless.
Yeah, because for global variables we have constructor and destructor.
Yeah.
So for but cleanup can be used.
For other kind of variables that
Yeah.
live in a scope well defined.
So if I have an if statement in my function and I declare a variable in that if statement, will the cleanup function be called at the end of the if statement or at the end of the function?
Because at the end of the scope, it has to be at the end of the
Of the
if
scope.
statement.
Yeah.
But surely you don't put cleanup on a variable, you put cleanup on a type, in which case it has to apply equally to globals when the after main exists.
I put cleanup in many places.
Yeah. So really the use case is for data initialization. You can do thread cancellation with that. It is the way to.
Basically, this slide is how to make C code do C++ stuff.
Yes, yes.
Use C++.
No. Next kind are attributes that have impacts on optimization. The first one is the attribute optimized. This one is used to define optimization flags at function level instead of the compilation unit. Okay, so you can apply the attribute optimize with just the number. I want 3, which means O3 on that function. You can pass the string OS. I want this function with the OS flag.
Can you pass 99?
Uh,
Some people actually do minus -099.
yeah, it will be O3.
I know, but you should error. Say stupid user.
We are not like that in GCC. We think our users are not stupid.
There was also PGCC which wanted to
Yes.
numbers above
Like you got your 03 and you could say go
It used to be
01.
different.
O1, it will be O1 for that function. After, depending on the
high levels.
sometimes there used to be bugs into this one. I think it is fixed now, depending of how it interacts because you can pass flags, like f loop optimized on this function. So how it interacts with the top level flags, etc. The normal usage is that the attributes will preempt the top flags of the compilation unit. But I know that sometimes it's quite unclear.
Can you use it for passing mfloat is equal to neon or something like that? Can I use that on a function like that?
You can pass the flag.
On a function.
But for
neon, so that will change ABI.
Yeah.
So it would
yes.
only so
but
there are options, compiler options that affect optimizations, and then there are that affect ABI. Only optimization flags are allowed in the optimized attribute.
Yeah.
Because they don't produce
Different code.
code for a different architecture or for a different processor.
Yeah, you can't change like minus m CPU equals arm or whatever arch.
You don't wanna do that.
No, that doesn't. Yeah.
yes, of course.
There is an exception for thumb and ARM modes, but because those modes were made to work together.
Yep. All of these one are to improve the optimization. It is not optimization flag. It is just you will give the information to your compiler that this particular function has this property. This function is a constant one. This one is pure. This one is no return. This one has no throw. It returns non-null.
What's the difference between pure and...
The pure added the possibility to look at the global function, at the global variables, to read into the global memory,
Right.
which is not the case of const, which is a function that will just look at the parameters and will have no impact than what it returns. Okay.
So for example, like const function, if it is called with the same arguments 2 times in a row, second invocation can be removed because it only depends on the input arguments. So
You can just save the value.
yeah, you can save the value and use it later.
Yeah. The leaf function are functions that are outside of the compilation unit and that will not come back through a callback. Okay. Malloc are malloc-like functions. No return. It's obvious. Assume line, etc. So this will really help the compiler to produce better code. So really, if you have the information that your function is const or is pure or is a malloc-like, you really have to pass it because it will really improve the way the code will be generated.
What will happen if you lie to your compiler?
You're a liar. So
Stuff will break.
yeah. So no return is one of the attributes that was added into C11, and you can ask GCC to suggest you to put attributes on your function. With this flag, GCC will tell you, hey, I think this function is pure, or I think this function is const. It can not do much than that, because maybe it's not, but it can tell you, and you can look at the code, say, okay, this is true, and you can pass the attributes, and your code generation will be better. Let's look at the ARM related one. The first ones, so these two are really ARM specific. Naked is a more generic one, but it is implemented on ARM. They will have an impact on the prologue and the epilogue code generation of your function. The use case is to use that when you are doing assembly code or programming interrupt handler, etc. So let's say, for instance, we have all the kind of attributes, a function without any attributes, one with the naked attributes, one with the interrupts, one with the IRQ, and two with the procedure called standard normal and VFP1. And let's look at the code generated. This is O0, so it is pure dumb assembly code. But the first one, without any attributes, you will have the Prologue that will look at the parameters, etc., and the epilogue that will restore the stuff. So this is the normal Prologue and epilogue code generation. With the naked attributes, you have just nothing. This is useful when you are doing assembly code, inline code in your C code, and you have to deal with the parameters, etc., on your own. Okay. For the IRQ one, it will do the context switch for you, prepare the context switch for you, push the registers, etc. Same for with the Prologue. And the last two one with the different procedure called standards. So the first one will use the general register to pass the parameters, and the second one will use the VFP1. On ARM, you also have two attributes to modify the calling sequence of functions, long call and short call. For instance, here you can define that bar L is a long call and bar S is a short one. And you will see that in the code that is generated, the call to bar will be done by passing through a register instead of doing a short call. Okay.
And
show the C code for the Prologue.
The first example? Previous? Yeah.
Very surprised you managed to get so much code out of
because it is O0. I compiled in O0 just to show you that there is a Prologue. If I compile with, it just disappears. I have to do a more huge example, and okay, for the presentation it's meaningless.
So a quick note about performance, relative performance of calling by a function and calling through a register is that on some cores will be smart enough to prefetch instructions through a jump or through a call if they have a constant address, but they may not be able to prefetch through a register. And yet, again, some processors will be able to prefetch code through a register, but not through a memory reference. So there are three grades of how fast you can do a call and how fast instructions on the other end of the call will start to be executed.
Yep.
Short calls are fast.
Yes. It is why on some calls you have some relaxation that when calls are done through registers, at link time you can identify that, hey, this function is not that far, I can do a short call, a relative jump, etc. And soon, okay, it may be in 5.1 GCC. The patch are under review. It's a target mode where you can change the function mode at the function level. Okay, you can say this function I want to have it in thumb, and I want to have this one in ARM. It can be useful in your code if you know that these functions will be in the code path of your execution, and you just want to reduce the size and put the ARM target on the function that needs more performance.
And it would possibly be an interesting optimization, like if a function has no loops, make it generated in thumb, and if it has
Yeah.
loops, possibly
Yes.
generated in ARM.
So yes, it will be soon available in GCC. And we have many more. We have some attributes to play with alignments, to play with hot and cold path, to disable some kind of path of the compiler, to disable the sanitizer on some functions, etc., etc. So, not sure you want me to explain all of them. It starts to be late, but if you have some question.
Why would I use attributes when I have pragmas?
There is, there is two kind of people in the GCC community. People that are saying that attributes are the new pragmas, that it's more well defined, etc. And some are saying that on some kind of stuff you have to use pragmas. So mainly attributes are replacing pragmas, but it's not true on all of them. And the kind of piece of code the attributes are working on is really well defined. It's function types, variables, and labels.
Well defined, but it's better defined. Than
Better defined, and it is really well defined into the standard with the new attribute into the
standard attributes are well defined.
are well defined.
GCC attributes not so much.
Not
so
so
if you
much.
apply to a, so if you have like struct whatever variable name, and you put the attribute in between struct and the type, and or after the variable, you apply the attribute in different parts of. So that is not very well defined, but it's still better than pragma, because pragma is in the preprocessor, and then you pass. So it's
Yes.
better. It's part of the language, not part of the processing of the file.
Yeah.
Which makes it.
And attributes can be used into macros.
Did the standard keep the guesstimation stuff through function pointers?
Sorry.
Attributes that apply to functions but not pointers automatically jump through function pointer syntax, even if you apply it to the wrong part. I don't know if the standard kept that or not. No, it's applying strictly to the right place.
How is it in LLVM?
We don't have GNU inline. I don't think we do. But
Any other questions? We still have a couple of minutes left.
Is it possible to have user-defined attributes? For instance, say I define an attribute on a function and write a GCC plugin to process that.
If you do the GCC plugin to implement it, yes. But you have to do the plugin. For the moment, there is no way to define your own attributes.
do you have a plugin architecture for attributes?
Yes.
Yeah.
Oh, that's.
Well, I'm sorry. I thought that we do. Do we?
I think so. I never used that. I never tried to use that.
It's one of the first things that it's easier in GCC than LLVM.
More questions? No, so now who is aware of attributes?
I have another. Who dreams up all these attributes? It's like who dreams them up? No ICF, no clone.
How?
So this is actually compiler itself. So when compiler does optimization and it thinks that a function has a certain property, like it is const, it will put a constant attribute on the function internally and use all the machinery to optimize const attribute functions which are defined with const attributes down the path. And so bunch of these, many of these attributes are made by compiler developers because they had optimization in the compiler already, so they just decided to expose it to the user.
Yeah.
Yeah.
Somebody asked earlier about when you lie to the compiler.
Yeah.
When you compile the function itself, surely the compiler knows it's been lied to. Will it warn?
Well,
Because
when you're working through headers,
Yeah.
when it's working through headers, it doesn't know it's being lied to.
So
But when it,
one case is the vectorizer, right? At least in LLVM, if you say to the vectorizer, look, this is safe in width 4, the vectorizer will still look for it and say, no, it's not. So stop saying it is. I will not vectorize this loop. So if it's clearly unsafe, you say, sorry, you can't do that. But if it's not clear, he will trust you.
yeah, and I was thinking about things like pure and const and things which are trivially checked.
Well,
Not trivially.
Well, you know if you're writing to a global variable, which is an obvious side effect.
so if you write to a global variable, you know.
Yeah.
But if you have some
Have it
mechanisms that
from-
may write, then you don't know. So
Like-
you have to trust.
Like you take a pointer to an argument, and then you do something funny with the pointer. If you tell that compiler that it is a const function, it will believe that you only do the pointer stuff and pointer magic, so that pointer still points to the arguments, not somewhere else in the program.
In the previous stack frame.
Yeah.
Yeah.
Yeah, okay.
Okay. So who will use attributes? Okay. Thank you.